All right, and we are live. Welcome to the Kubernetes on Bare Metal webinar. If you wanted to learn how to run Kubernetes on Bare Metal, what the pros and cons are, this is the webinar for you. My name is Kevin Reeuwijk. I'm the principal architect at Spectro Cloud, and today I'm joined by Craig Bender. Craig, you want to introduce yourself?
Sure. Craig Bender. I'm a field engineer with Canonical. I'm based out of the US, and I've been with Canonical for about 8 years now.
Great. Happy to have you. So what we're talking about today is what most Kubernetes deployments look like today. Spoiler alert, a lot of them are not bare metal today. If there are benefits to running Kubernetes on bare metal, what considerations are when you try to do that, when you try to design bare metal Kubernetes clusters. And then we'll take a closer look into how Canonical MAAS can help you solve that problem and why we at Spectro Cloud like Canonical MAAS so much that we built an integration for it. And then we'll go a little bit deeper in if you start phasing out the traditional hypervisor for your Kubernetes cluster, at some point you can also ask the question, what about then virtual machines? What do I do with them? And we have an interesting response to that as well. During the session, if you have any questions, please ask us. There is a question mark in your GUI, the question section. Just hit putting your question there, and one of us will pick up the question and we'll try to read and answer them during the session. If not, we'll pick them up afterwards, but ideally we will answer them during the session. So keep the questions coming. All right, so what do most Kubernetes deployments really look like today? Well, a lot of them, probably most, are on top of virtual hardware. It seems most deployments of Kubernetes are happening on the public cloud platforms, where you can easily request a managed Kubernetes service that gets spun up for you. All of these platforms, of course, also allow you to build your own cluster with VM instances if you prefer that. For on-premises, that's exactly what most companies do. They use something like VMware or Citrix or KVM to have similar cloud-like platforms on which they can deploy VMs, and then they build Kubernetes clusters from those virtual machines. So a lot of these Kubernetes clusters in practice are built on virtual hardware. And if you think about it, for cloud platforms, it actually makes a lot of sense to run Kubernetes on those cloud platforms, as it is a great way to deliver on this whole fabled multi-cloud strategy that many companies aspire to, but for most turned out to be very difficult to achieve due to the complexity it brings to work with all of these different cloud technology stacks. But if you just run Kubernetes on each cloud, whether it's managed or unmanaged, then you only have one API, namely the Kubernetes API, to interact with for your applications. So that makes a lot of sense. But what about on-prem? Do the same benefits apply there? Well, not as much really. Most don't really run more than one virtualization platform at scale in their own data centers. Sure, that maybe you'll find some alternative platforms in small pockets here and there, but for the most part, let me change the layout to full here. There we go. But for the most part, it will just be like a single platform that gets standardized on. And the reason why I'm singling out VMware a little bit here is because that is the platform that most tend to run. And it's the company that it has its customers a little bit worried right now as to what will happen to it after Broadcom fully takes control of it. But let's come back to that specifically a little bit later. For now, let's discuss on what you have a on-premise virtualization platform for in the first place. So you have it for abstracting your hardware. So it becomes easier to, there we go. So it becomes easier to deal with for the average internal end consumer. After all, VMs all look alike, and the internal end consumer doesn't really have to worry about drivers, firmwares, capacity management, and everything else. Another one is making deployments go faster, as it's much quicker to create a new VM than it is to order and boot a new physical server. Another is improving availability through things like VMware HA, vMotion, allowing you to recover from hardware failures much more easily. And the fourth one is increasing utilization by running multiple workloads on shared hardware. This has actually been a major driver for virtualizations in the 2000s and the 2010s, as the reduction in hardware footprint and power consumption could often just pay for the technology outright. So this is all great functionality, but it also costs money. And companies like VMware have made a very good living selling this to us all over the last 25 years. But these are all core capabilities that Kubernetes already delivers itself for containerized workloads. Kubernetes abstracts hardware, allows you to define how much resources to use for each workload. Kubernetes deploys workloads even faster than VMs, as you no longer need to install an OS anymore, and it can spin up the workload anywhere in the cluster. Kubernetes recovers from hardware failures on its own and does not need vMotion to ensure applications stay running during maintenance or hardware issues. And Kubernetes gives even better use out of the hardware, as the overhead for containers is much less than for VMs. So a legitimate question to then ask is, do you really need this virtualization layer in between for your Kubernetes clusters, especially the on-prem ones? If all the internal end consumers interacting with is the Kubernetes API, wouldn't it just be simpler and cheaper to just run Kubernetes on bare metal hardware directly? I mean, it's certainly an interesting idea, is it not? So let's explore that in a little bit more detail. There are definitely benefits to running Kubernetes on bare metal, but performance isn't one of them, at least not really. So taking away the virtualization overhead will net you a little bit more performance, but don't expect more than about 2%. There are situations where the last 2% is entirely worth it, but for this presentation, we are not assuming that that is the case. So what are the benefits then other than slightly better performance? Well, for one, resource efficiency is better, since you're not artificially slicing up real hardware into VMs, only then to group them together again into a Kubernetes cluster. So you should be able to run about 10 to 20% more workloads on a bare metal Kubernetes cluster compared to running Kubernetes virtualized on the same amount of CPU, memory, and storage. The total complexity of the solution is lower as well, as there is just one orchestrator at work instead of two. No need to worry about underlying vMotion or DRS interfering with the state of your Kubernetes cluster, for example. Every host is also guaranteed to be an actual physical server and thus a single fault domain, excluding things like power or networking going out for like a whole section of the data center. So in contrast to when your cluster nodes are virtualized, some may actually be running on the same physical node, and most likely some will be running on the same physical node. So if a physical node then fails, you can have a bigger impact than you designed for, taking down applications and services that would have survived a one node failure in a physical cluster. You also got very fine-grained control over resource reservations, like CPU and memory, that actually work the way that they are intended. When CPU and memory resources are virtualized, you have less control over other workloads running on the physical host, the so-called noisy neighbor problem, making Kubernetes only able to see part of the whole picture. And you don't have that issue when you're running on bare metal. And the same goes for having insight into the status and performance of the actual hardware serving your workloads. Without virtualization, Kubernetes performance metrics reflect the actual performance of the hardware, not the performance of virtualized resources. Alerts for like disks becoming unhealthy, like from smart data, are also no longer hidden from Kubernetes and can be reported on directly. So let's consider then what you have to what do you have to take into consideration when you're designing a bare metal Kubernetes cluster. So running Kubernetes on bare metal is all about being able to control and especially automate the hardware and OS configuration. With virtual platforms, these things tend to be further abstracted away and they do not require as much thought. For example, on a virtual platform, it can be fine to have a single virtual NIC in your VM, since the actual resiliency is taken care of somewhere lower down in the virtualization platform. But with bare metal, we actually have to account for the resiliency at a hardware level ourselves, through things like network bonding and storage multipathing. So we need to get the correct software installed and configured when deploying these bare metal servers. And we want this to be fast and consistent as well. Clearly, manual deployment and configuration is out of the question if we want to do this in a good way. So how do you solve this problem? Well, Canonical, of course, actually provides a wonderful piece of software that everyone here at Spectro Cloud has completely fallen in love with. It is called MAAS, for Metal as a Service. Let me just hand it over to Craig Bender, Distinguished Field Engineer at Canonical, and member of the MAAS team directly to tell you more about it. Take it away, Craig.
All right, can we go next slide? Perfect. So question, just to start off with, to kind of tie this together, why do you think public clouds are so popular? Okay, next. And it's really just like it's not about the performance on bare metal Kates. It's really not just about the price. Sure, there's OpEx versus CapEx when you're first starting out. That's why startups tend to like the clouds because they don't need that big outlay of cash to buy hardware. But the reality of it is that you're able to get to your machine faster, right? Besides cost, the beauty is that I've seen those two lost. There we go. If you look at the difference to spin up a machine, quote unquote, or an instance on the cloud, a public cloud, it really, it's a few lines of a command. If it is bare metal, we have some customers that are up to like 9 months to a year on their procurement process for bare metal. So besides just the justification on purchasing, things like that, you have a lot of time, a lot of waiting. Things like the pandemic with supply chain backlogs didn't help out as much. I'm sure everybody looked at what GPU prices were, and even Raspberry Pi still haven't even recovered from the pandemic. They're still at least $30 more than they were pre-pandemic. So they were at a time up to, I think, something like $300 versus $75. But people want this hardware, and it's not available. It slows it down, so it just exacerbates the problem of cloud versus metal when we run into situations like we just saw. Next slide. And the time, right? So it's about working, getting your stuff done versus waiting on things that just aren't, don't help your business at all, right? So about 4 minutes to deploy a machine in a cloud versus 4 months. We actually have one customer that they have a self-provisioning system for VMs, but it's tied to metal on the back end, and they needed more metal. They were on a 6-month VM assignment, which is kind of crazy, but that's the reality of a lot of corporations today. We go to the next slide. So what we like to say with MAAS, it's a bare metal cloud, right? So if you want to kind of deploy almost any OS to almost any piece of hardware out there, MAAS is what you want to use. So we basically provide MAAS or cloud images for most major operating systems. So we just added SUSE in the Linux category, as well as Rocky in the Sense stream. So we'll be expanding that picture out a little more, but you get the gist here that plenty of non-canonical based OSs can be deployed with MAAS. And we have some customers that deploy nothing but Windows with MAAS, right? And the reason why is that when you're dealing with a cloud image, which is basically a pre-installed hard drive image that gets customized through tools like Cloud Init, you don't go through that whole ISO installer process. So one company that we working with took their Windows install time from 45 minutes on an ISO-based install to 15 with MAAS. And that's a pretty huge savings of just getting things into production, getting into the hands of the developers, getting into the eyes of the users. On the back end, on the hardware side, MAAS is pretty much the kind of requirement is basically it has a baseboard management controller, BMC, something like iDRAC, AMT, IPMI. Those type of things are what you really want, because that's kind of magic to run a lights out data center, is not having to send somebody in there to push that button. The only thing you want people to do in a MAAS environment is rack and stack. So your rack and stackers will go put a server in, and then you turn it over to MAAS. And MAAS can do pretty much everything that your rackers and stackers used to do, except tighten the bolts and put it into the rack itself. Go next slide. So how we use MAAS is one of our core primitives in our field engineering team. So we have a few things that we deploy no matter what we're doing from a professional services standpoint when it comes to cloud. So whether we're building a microcloud, Kates, microkates, or OpenStack, it all starts with MAAS. So unlike some other tools out there, you don't need a cloud to deploy a cloud. So MAAS can run in a VM, can run on a small piece of hardware, and then from there it can bring up machines that turn into clouds, right? So you can MAAS as a standalone can be extremely powerful. You can use cloud in it and pretty much do everything you want, but the real beauty comes when you pair it with an orchestration tool. So here we'll be showing Palette. We do have, if you go to github.com/MAAS, you'll find that we have Ansible playbooks, we have Terraform providers, and traditionally we've always, Juju's always supported MAAS. But MAAS is a very robust API that's moving to Swagger Open API soon, but right now it's a full REST API that most things can consume. Ansible is very aware of it. OpenStack Ansible uses MAAS on the back end of provision. Many things use that. So the API is robust. It's well used by everything out there from Puppet to Ansible to Juju. Go to the next slide. And some of the features of MAAS, and this is where it kind of gets into that, you have better things to do than probably, deploy hardware. So MAAS tries to take care of that for you. So from a standpoint of what power drivers or VMCs do we support? If you look at MAAS, there's a list of pretty much everything out there from at the machine level to the chassis level. So different zeros, if I'm going to go tell a machine to power on or inventory a machine, I talk right to that VMC. A chassis, something like a UCS Manager or Moonshot, I basically query the rack, and the rack is an intelligent rack, and it tells MAAS about what's in each at each U level and gives me back an inventory. The speed of deployment is pretty incredible. So you should be able to deploy almost anything minus the post time in about 5 minutes. A little faster if you have NVMe or SSD where it's laying it down. And some of these servers out today, the longest part of the deployment is actually the post. Watching the memory count, going through the UEFI loading the daughter boards and whatnot.
Yep.
What you get, go ahead, sorry.
Yeah, for sure. That's definitely the thing that takes the longest compared to watching a VM boot.
Yeah, it gets you do get a little tired of seeing it, but that's why you kind of just hit deploy and go grab a cup of coffee for the first couple minutes.
We also got a question from Jeremy. What version of MAAS are you on, and do you stay current?
So I saw that, and I thought we could answer that two ways. What is the CAPI provider support, even though we haven't jumped into that yet? That's one answer. But I stay current. I'm on 3.4 beta 3 right now, and I believe Kevin is as well. And because my job is to basically make sure that everything we do in the field, the next versions are going to work with it, right? So I'm always looking at the new features of MAAS. Plus, I have customers that are always waiting on the new features. Just one that I've worked with recently was really waiting on Celeste 15 support in MAAS. So I had to test that early, and that required 3.4.
Yeah. We also stay current. We actually had a bug in 3.2 that was fixed in 3.4 beta 3. So we are definitely following it closely.
When one of the benefits of MAAS too is you get a full inventory of every machine out there, and one of the kind of recent features in the 3.x timeline is we basically now inventory every single PCI and USB slot. And why that's important is in the world of clouds, in the world of Kubernetes, and world of things like OpenStack, whether I'm passing through a driver or I'm passing through a PCI slot, I need to know that information. So think about something like crypto mining today. These big, huge farms, companies that have things larger than a Costco that are nothing full of machines doing mining. And you need to go get all the PCI IDs off that, and you want to be able to pass those through. Or in order to do that, you have to tell the host that GPU is running on, that to not use it for its local resources, right? So don't display video through it. I want to save this. So you have to go basically create an isolation list. And how that's done today is people go, they install the card, they go boot it, then they go do an LS PCI, they get the ID, then they go edit something like Grub, then they reboot, they get it wrong, they had a typo, they do it again. It's kind of a science project. If you go just Google, GPU pass through, and you'll find 20 different ways to do it. The beauty of MAAS is that we're going to have those IDs. We can do the scripted, we can do it automatic, and we have things that are basically called like a tagging. So if you think of any type of hardware inventory listing, in this case, it would be LS hardware. So if you're looking at any XML element in an LS hardware output, any of those can be used as a constraint in MAAS to assign a tag. And a tag is more than just naming it. A tag can have different kernel options, which in the world of Linux and Unix is extremely important. So in a kernel arg, that's where I tell it, not to use my NVIDIA V100 for, that's a data center role. Don't use my RTX for local video. I want to make sure that it's just either I have no video or I'm going to use the onboard VGA, but I need to have this thing not attached to the kernel, not attached to the driver, so I can pass it through to something else. Whether that I'm passing through the CUDA driver to Kubernetes, or I'm passing through the whole physical PCI slot to a VM, it can't be taken by the host OS. So MAAS can do those type of things. It can also do different tags and different arguments just based on hardware. So imagine you have a server with 10 8 terabyte SSDs in there. You might want to tag that as a Ceph node. So when you go use your orchestration tool, something like Terraform, Ansible, you just say, use a constraint called Ceph node, and it goes out and finds the right server for you. Above and beyond that, we control all kinds of storage layouts in MAAS. You can even lay down vCenter file systems. MAAS to be and tends to like to be the IPAM for the subnets that it's on. Does not have to be. You can use your own DNS. Traditionally, how you'd want to do DHCP. Traditionally, you'd want to use something like IP helper, DHCP forwarding for that to work, at least on L3 subnets. But on L2s, you can basically give it the next server argument and point that at as a MAAS rack controller. MAAS it does a very good job of being an IPAM. It comes with a full enterprise DNS server, and you can kind of use it as a source of truth for your network, and then or delegate to your corporate DNS if you want to. And then one last feature on this part, hardware testing. And we'll talk about the scenario right now, but MAAS can we give you a predefined set of hardware testing burning type scripts. So you could get a rack of servers and run scripts for like 72 hours. And once it's done, it's either going to be pass or fail. And then you can say, hey, I've done a burning test. So imagine getting a rack of servers. It's on the dock. It's got to go in production next week. You want to make sure they have burning tests. You want to make sure they, everything's working. So first thing you do is just basically rack, turn them on. MAAS will PXE boot them, and then they'll run their hardware burning testing for 72 hours. That's not a requirement, but it is a good idea.
Okay.
And next slide. And then we'll just cover a couple things here. The most interesting things here is that from a MAAS standpoint, if you're familiar with it, out of the box, it basically has a local account stored in Postgres. You can tie that into your own authentication source with, and this is for customers with support. We provide middleware Candid and Canonical RBAC for our customers with support, and then you can basically log into AD or LDAP or things like that instead of just to the local Postgres account. And that's I think the one part where people aren't aware of that. So I wanted to share that. From a standpoint, again, the GitHub/MAAS, you'll find our Ansible providers and our Terraform, or our Ansible playbooks and our Terraform providers. And then one of the things that we'll kind of touch on here, since we're talking about clouds and mini clouds, micro clouds, on-prem, MAAS has the ability to do what we call KVM microclouds. So whether it is libvirt managed KVM or LXD managed KVM, MAAS can actually deploy a server. So you basically deploy an Ubuntu server. You click a box that says turn this into a KVM host, and you choose which power management you want there, whether it is LXD or libvirt. And MAAS will turn that into a hypervisor that when you define machines on there, they come back into MAAS as machines ready to compose. So you're basically carving up metal into smaller machines and giving those machines out to whoever needs them. And we'll see that here, a little bit of a demo.
Yeah, this is actually really useful to, for example, run Kubernetes control plane nodes as VMs, since they don't need a lot of resources, and allow you to keep your big bare metal servers to run as worker nodes.
In fact, we do a similar thing. For those who are aware of the Juju product, it has a state engine. We call it the Juju controller, and we usually boot that up, at least in kind of test out lab environments, just a single VM on the same thing as the MAAS server. But actually, in the field, when we deploy our enterprise grade primitives, or we call it our infra servers, it's basically out of N+2, we have those. We basically have our Juju controller. H8 across those 3 bare metal servers. So it saves up, it not only saves resources on your real servers, I guess your production load servers, but it's actually quite handy and very fast.
Yeah.
We'll cover the architecture here somewhat quickly, but I won't go into the demo here. A high level, there's basically 3 tiers at the MAAS. There's the database tier, which is Postgres. Version depends on the version of Ubuntu that you're deploying MAAS on. So it could be anywhere from, with 18, I think it's 10, and then Lunar is now 15, right? So the Postgres usually gets upgraded. MAAS does a very, very good job of keeping Postgres updated. So when you go to upgrade your MAAS and it says that you need to upgrade Postgres, and if you do that, MAAS runs all the mitigations for any changes to the schema. and I've never had a database. And this is going on 8 years, and probably installing MAAS at least once a day on average over that 8 years, minus weekends sometimes. I've never had a database problem. So some of that is due to the Django database tools that are in use there. The other part is just some very good developing from our team there. But with Postgres, it really is the most important part of the whole scheme. And I know that might sound counterintuitive if we have things that are actually deploying, but that's where our entire state is, from the inventory to the images that we're using to any kind of changes that we're making to the machines. Everything is stored in that database. The controllers themselves are fairly stateless, with the exception that the rack controllers have a secret on them, so it can join a region, right? So with that Postgres side, we like to do like an N+2. You can do an N+1. It should be on the same subnet, absolutely. You can do HA with the distributed across L3. In that case, there's different rules in Postgres, but something called a witness node. It's not a full node, it's just a tiebreaker. You can do those things, but it's usually simpler just to do N+2. And Postgres is one of those things, and most DBAs will tell you, they don't like automatic failover. So how we usually design it is basically to get everything ready, but not do that promotion until a DBA has a chance to look at lock files, look at who has the latest thing. We don't want to wind up with sharding, which is a reality in the database world. But the care and feeding of Postgres there, to me, is critical for a successful MAAS deployment. Next thing would be, how good is your network? MAAS goes as your network goes. So if you have a lot of retransmits, drop packets, things will go slower with MAAS. The next level is the region controller. Think of this as really kind of your management endpoint for both the database, for the machines. It has some of your core services that would rely that everybody would use, regardless of whether you're deploying, whether you're configuring or whatnot. But there's a DNS server that's all done there. There's also a caching squid proxy on there so when a machine goes out to our archive and pulls down a package, the next guy that does that can use the cached package. It also provides the API interface and the web UI. And finally, the rack. Go ahead, sorry.
Yep, there's a couple of questions coming in.
Here we go.
Let's see. One question is, can PostgreSDB be on SaaS in the cloud? Since PostgreSDB HA is a bit complex. I guess that's possible.
So we do that. We have a couple of customers that are using Amazon's database service, and in that case, they do Postgres. And if you've looked at RDS, you could know that they have every single major and minor release of Postgres up there that's available to go, and they do make HA very very nice. The beauty of HA and how we deploy it is because we have the machines there, and otherwise they'd be sitting idle, so we kind of use it there. But honestly, if you have decent pipe, or you have like an S3 bucket up there on the cloud, even you can almost get away with just basically doing a base, what's called a PG based backup, which is how you start off the synchronization. You basically copy one to the other, then turn on streaming. If you just did that on a cron job up to an S3 bucket, like 30 minutes, you're probably going to take about the same time to restore. After you've done, looked at comparing, who's got the latest tables, looking at lock files, things like that. If you just know it's a good backup, you just, don't even worry about checking it, just reinstantiate that database. And to me, that, maybe it's not as enterprisey as an N+2 cluster, but it's faster. And it, technically requires less expertise to do. Just cron job running a PG-based backup, and it doesn't get much simpler than that. So.
Indeed. There's another question. I think this relates to availability zones. The question is, if I do carve up some machines into hypervisors, can MAAS guarantee that my Kubernetes masters for a cluster are not on the same host? This actually ties into how Pallet works with this. So what you would do is you would have, for example, 3 bare metal hosts that you would, all the VMs that you create on one host, you would put in one availability zone in MAAS. And that way you would have 3 pools of VMs in 3 different availability zones. And then when you use Pallet to deploy and you select all 3 availability zones for your control plane, Pallet will automatically spread out the nodes and make sure that it uses a node from each availability zone.
And ideally, that's how everybody should do it. The fact of the matter is most people don't have separate power and network going to each AZ, but it is a good idea to have that practice just to get used to it for when you do have that. You're used to using it, because what happens in an AZ, or what people don't think about, your AZ should be balanced. And what I mean by that, let's just say we have 3 classes of servers in there. We have general class, we have a compute intensive, lots of RAM, lots of CPU, we have storage servers. I could go and basically tell it that I want to use this type of server. And if I declare the availability zones, it's going to try to do what Kevin said. It's going to try to balance that out. So it's going to try to, let's say we don't have any storage servers in AZ1, but they're all in 2 and 3. It's still going to try to look every time it goes to balance it out. And it winds up taking longer to deploy if you don't have those balanced AZs, because it'll basically, every time it'll try to find that to balance it, find that AZ that doesn't have a machine in it. And it'll keep doing that. So make sure your AZs are balanced is a caveat, but it's absolutely a great idea. Even if you don't have separate, whether it's geographically separate, whether it's power and networking are separate, it's a good practice to get into, because things like Palette make use of them. Right? Juju does as well, and I believe Ansible will as well. So you can, if AZs are in use, it's usually an automatic thing unless you tell it not to worry about it, right? So, or not to balance them out.
There's also a question on what the flow looks like to get the hardware like properly configured in MAAS. Like there's many things to configure, of course. And I think your demo will go into that. So maybe better to showify the demo on how you can automate that kind of work.
Right. So I mean, we could look at the answer that partially before the demo. There are going to be some things that MAAS can't do, and that's mainly involves like racking and stacking. The other thing would be is that if you have some BIOS, or let's say we're legacy, and then there's instead of doing it through the UEFI BIOS, I'm running this machine's legacy. I have to go into a Mellanox card or something to go into its internal BIOS. Mellanox is a bad example because they actually have very good Linux support, but let's just say they didn't. That would be hard for me to go configure that card in a Linux environment if I didn't have any kind of utilities, right? So those are kind of the things that MAAS would have trouble with, but the fact of the matter is almost everybody has a Linux or API type call that can be made, whether it is through curl or whether it is a straight binary command to run. So those things are a big deal. But configuration of just general configuration of your BIOS, switching it from legacy to UEFI, setting the different PXE NIC, maybe turning off some PCI cards, PCI slots while it's booting because I have power problems in the data center. Those are stuff people would normally do, a racker and stacker, and then they'd probably lay down the OS too, and then tell somebody it's up. In MAAS can do all of that, right? As long as there are those binaries or there's an API. So we do iDRAX, we do HP Rust, Lenovo. Basically, you set the BIOS the way you want it. We can do RAID configuration, HP Smart Controllers, perks, JBoss. Those things are kind of part and parcel, and that's through what we call a commissioning script. And I'll show a little bit of that.
Cool, thank you.
I think talked about this part. Let's go ahead in the next slide. I think we covered that. The big difference there on the rack, I didn't mention that. Go back one if you could. At the rack level, go back one more. I forgot one thing. So at the rack level, this guy does the heavy lifting, right? So a lot of the services you kind of think of a MAAS as a magic curtain in front of some ugly services like PXE and TFTP and UEFI booting that are a little bit complex to configure and get working in lockstep, especially on the fly, rather than somebody sitting down and writing a fairly decent long DHCP conf. MAAS is doing this all on the fly based on machines that you're telling you want to deploy. So it's grabbing that MAC address, creating a record on the fly. It's doing a lot of things that would that is prone to typos, right, and prone to scripting errors, and it handles all that quite beautifully. And then from a standpoint of deployment, we'll cover that in a second. But when we talk about subnets and VLANs that MAAS deploys to, whatever's directly connected to the rack will be auto-discovered. And then if there's anything L3 connected, that would be defined by administrator. And let's go next. We'll talk a little bit how we HA this. Again, the database, you can do an N+1. The technology there is wall streaming. There's two styles of Postgres. There's what's called async and sync. If you only have two, you want to do async, because what happens in synchronous is that if that secondary goes down, the primary won't write until it's back up in a synchronous mode. So if you're async, it'll let it write even, well, they won't be able to write if there's nothing to write, but if you fail over, one gets locked, right? And that's a bad scenario. So we usually do, in an N+2, we'll do one async, one sync. So we get that millisecond difference or so on the right, but then we allow the cluster to keep working should one of them go offline. Traditionally, we'll deploy this with a VIP, so that all three nodes, the virtual IP will be owned by the current primary, and then the secondaries can be used for like read type situations, but only writes will be happening at the primary. All the region controllers then point to the VIP, and that's a fairly easy way to do this to make sure that you're doing. And all the services like the DNS and NDP that is provided by the region controllers, should you want to consume those, would be available at the same VIP. So even if we fail over on the N+2, it's always going to be the same IP addresses there. So that kind of moves us at the region controller there. Regions are all active, active, active. You get multiple region controllers. Inside of the region controller, or the rack controllers, they talk to a list of regions. So if you want to do kind of like least cost routing, you can alter the list of rack controllers to always go find the closest region. But there's regions don't have to be any kind of like active standby. Racks are a little bit different because services like DHCP and TFTP and things like that are basically active passive. We can't have two sources of truth when it comes to DNS out there, just like we wouldn't want two DHCP servers offering up addresses. So those are and this happens on a per subnet basis. If I have 10 subnets defined and I have two rack controllers, I can alternate between those subnets, which one is the primary rack, which one's the secondary rack. And one will just sit there and be standby until he senses that the other one's not there. They do discover each other if they're on the same L2 connection. So like I have two rack controllers on the same L2 subnet, it'll basically, when I go to create or provision a subnet, it'll offer me multiple rack controllers for that, and I can pick my primary and secondary. And next. And this is kind of how we handle the provisioning at the HA layer. When it is L2, that just automatically fails over in the active standby, but L3 is a little bit different. So how we handle L3, since there's not that direct L2 connectivity for it to do discovery, on your router, you basically have a helper address for things like DHCP, and you just point that at two rack controllers. And it'll basically, the first one that answers, the other one, it'll disregard, it'll NAC the second response. So you're always getting a good response. If the one of them is down, it'll just hit the other one. And that's how we kind of handle it there. It's not as true HA as an L2, but it works extremely well. And next.
All right. And
there's a couple links here. There's a tutorial that gets you going in 30 minutes on MAAS. There's a script repository. If you're looking at, hey, I want to basically configure this HP RAID controller, or I want to do this Mellanox card. We have examples up there. Dell iDRAC upgrades for some 40Ds. Just pretty much anything that I do, I throw up there in the field. And so you can use that. There's a lot of metadata inside of what we call our commissioning scripts. You'll see both kinds. You'll see scripts that have no metadata, scripts that are very specific to a certain motherboard. And so you can basically get down in these scripts and say, this script is only for a type of server that has this product number on its motherboard. Or you get down to PCI slots. Only run this if this vendor and ID. Sorry, product ID is in my PCI inventory list. So you can get really granular on those scripts. And then the next thing is one of the most powerful things in MAAS is the XPath auto tagging. And I'll show an example of that. Not a lot of people use that, but again, this is that where we're looking at an element in LS hardware, and we're going to use that to basically control how the machine boots.
All right, do you want to share your screen?
Yep, I'm going to share here. 1 second. Let's see, where did I put my screen? Oh, there we go. All right, so here is our MAAS 3.4. These are machines that I basically pulled into MAAS already. And what I've done here to bring these into MAAS, you do it a couple different ways. I've actually just sideloaded these, where I tell it the MAC address, the credentials, MAAS can turn it on, and then it goes through and does an inventory of what happens. When it does this, we call it commissioning, but it's really an inventory. It does a few different things. It installs some binaries out there to help it better understand how it's connected. So LLDPD will tell you what switch, what port you're connected from a network standpoint. We'll go ahead and get all the dump of the ports, the disks, and everything. But we kind of look at this output here. Right? So any of these elements, if I want to say, hey, if it has this product, let's tag it as a NUC, right? Or if it has just even starts with the word NUC, we'll tag it as NUC. And you might say, well, why is it important to know, it's a NUC or it's just a standard reference Intel board or it's a Dell. Different things use different serial ports. So if we want to do serial over LAN, we want to be able to watch that console, again, where lights out. I need to tell it what the console port is. AMT, which is the baseboard management controller used in NUCs, it's also called vPro now, or vPro Enterprise. Basically, that uses TTYS4. It's the only thing out there that has serial port 4 for the serial over LAN. And the danger here is, like, if I go to start and I say I'm just going to assume it's TTY1 or TTYS0 or TTYS1 for the serial over LAN, it's going to sit there and try to talk out a serial port that doesn't exist. So think about every single message when you're booting up. That's going to get basically denied. Try and talk to serial port. Your install is going to time out. It's going to take hours. So it's kind of critical not only for just remote management to have that right console port set up, but it's good for installation speed. So what I can do is I create a tag for anything with a AMT controller, and it's going to get automatically tagged. So let's kind of go walk you through that. So I'm going to create a new tag, and we'll call it AMT, or we call it vPro or whatever. In this one, you don't have to assign kernel options, but I want to. So what we're going to do here is we're going to assign these kernel options. We're basically saying, hey, if it's a physical, use TTY1 because that's the display port on the NUC. But if it's virtual, if I'm coming with serial over LAN, I want you to run on TTYS4. Right? Then I'm doing things like I'm turning Intel IO MMU on, and I know it's going to be Intel and not AMD because it's a NUC, right? And then KVM I want to set up for nested. So in case anybody happens to run a VM on here, then they want to nest a VM in there. It'll have that hardware acceleration. So I just want to pre-do that so they don't have to go into their host afterwards and reboot it, right? And then so here's our definition of our tags. We basically just do an XML argument. And all I'm doing here, if we kind of remember back, I'm looking for a product that starts with NUC, and then it has a class of communication called a MEI controller. And that's basically my argument. And in this, how I test this out, you could use like XML Starlet, XML Lint, just different utilities out there to kind of tell you if your XML query is working. So let's go really quick. I'm just going to launch. Actually, I'm going to save this. So we just created that new tag called AMT. Now let's go look at these machines, and it happens really quick. So these tags should come back through here and start tagging ourselves as AMTs. Let's go and see if it got tagged. Might have got something wrong with my tag there. Hold on a second. And sometimes it takes a little bit for it to show up, but they should show up. I mean, because this basically absolutely meets that class. So we'll see what happens there. But what happens, all these guys will boot with that tag. Now, if I want to just have general kernel arguments, I can do that. Right, and so this will be like everything that doesn't have its own set of kernel args. It'll basically default to something like that, right? And I could put a console statement in here should I want to. Let's go ahead and let's do. So let's check these machines are new. We're going to go through and commission them. And this is basically just saying like they're brand new. MAAS doesn't know anything about it. It's going to go power on all the machines, and it'll run through those little scripts we saw in the commissioning. So everything from grabbing the network information to the disk layouts. And what happens there? We have a to-be-built record. And that to-be-built record, I can make all kinds of changes to it. I can do different disk layouts. I can do bonds. I can do bridges. And then from there, I have this record. And when I click deploy, that's when it actually makes those changes to the machine. And it does that through a couple-step process. So kind of high level what MAAS does, powers on the machine, does a Pixie boot of the machine, downloads a network-based kernel. And then from there, we run a RAM disk, right? So a little ephemeral image boots up. That does nothing but basically copy down the image you want, does some configuration, pre-configuration to get things right. Then it will reboot. When it reboots, it's laying down lays down the correct file systems as you've defined in MAAS. So you don't actually define a file system like in the MAAS image. You do it at the machine level. So it'll adopt your, like say we keep bar separate, you keep user separate, it'll adopt that based on your layout of the machine. And then it'll do any kind of customization after that with Cloud Init.
There's a question from Jeremy. Is there a rule of thumb for how many machines a single rack controller can manage?
So the rule of thumb is 1,000. I would say simultaneous deployment, 100's getting there. There's a lot going on during that initial kind of boot network traffic. Some of it depends on your network. If you're 10 gig or higher, 100 is not bad. 100 pushing on a 1 gig or 10 gigs getting a little full. But usually from a standpoint of what it should manage, we like to go with 1,000 per rack controller. And
I guess it mostly depends on how many are
simultaneously deploying. Yeah. So simultaneous deploying, I like to keep it in the sub 20 range, but that's just my preference.
Got it.
So we kind of look through what's happening here. So you saw boot Pixie. It loads the ephemeral image, and then if we kind of go in there, you can watch logs. There's a full suite of observability tools, including Grafana for graphing that you can set up that's provided with MAAS. But sorry, go look at logs. We can watch step by step what's happening here, right? Each step of Cloud Init is documented, but we see where we powered it on. This is what the machine requested from a standpoint of its information. You can see what's happening over TFTP versus what's happening with HTTP. As we move more towards Wi-Fi pure booting, getting away from legacy BIOSes, we'll see Pixie disappear from the world, and things will be more secure. TFTP is just not very secure, but it's a requirement for legacy BIOSes. Again, so all these different packages, and then you can see that's going through the scripts now. So it gives you green that I passed everything. Right, and then finally it does a couple little hardware tests just to make sure things are working. So if you have a smart controller on your disk controller, it just does that simple test to make sure that we know if this disk is getting old, if it's having any kind of heat issues. It's basically smart tools for your disk system. So it does that test. What if you don't have one? It'll just skip the test, right? So if you're on a VM that does not have that type of hardware, you'll just do it. Now what'll happen? So it's finishing commissioning. It moves them testing, then it marks them as ready. And ready, now I can go make changes. So let's say I want to go create a bond or a bridge. Let's say I want to create a bridge on everything. I create a BR0, I put it on the subnet I want, and I say what kind of IP I want to give it, and I save that. And it's gone basically, I haven't done anything to the server. Again, this is a to-be built record. Now when it comes up, it'll have a bridge off of this NIC. Another thing that happens in clouds a lot is I usually use a second NIC for some kind of, whether it is a replication or whether it is a public type access network or overlay type tenant network. I need to know the nickname. If I have these NICs that are basically going to be different for every server, so if I come in here, this is ENX, it's basically ENX and then the MAC address, any USB-based NIC. Granted, that's not enterprise, but you will see different naming systems, even across, you can have the same Mellanox card across two different vendors, different PCI slots, you're going to get different names, right? So I might want to go rename these so they're common, because I know I want to use this NIC, whatever it is, as my replication network. So what I can do there for a simple standpoint is I can just go in here and just rename that, right? So now instead of ENX1, I'm just going to call it ENX1. And if I do that across the board, then I know that what that NIC is called, but I'm going to set up open OVN or Neutron or something of that nature, or any kind of CNI in the Kubernetes world. I know what NIC, what is my physical network NIC. I don't have to go guess per server or go look it up. So I can do that change. So when this gets deployed, it'll show two NICs, basically BR0 and ENX1. And that's a lot of pointing and clicking. So I can do that from an automated fashion as well. So what I'll do here is, let me switch screens for a second. All right, so just a couple of little utilities are written, but we have a little one that I called MAAS. Let me source this. This is going to pull out all the information about the MAAS NICs that are out there. Bigger. So you can see what's happened when I've dumped the information. I have a system ID, the NIC ID, it's MAC address. So I'm going to go rename everything that has an ENP, and I want to create a bridge. So what I'm going to do is kind of that same command, pull some fields out, and then I'm going to run the MAAS command. So think of this as a CLI or API access. So again, right now we have only one thing has a bridge on it. Now basically I'll get one error that there's already a bridge, but that's okay. And it's going to basically go through MAAS and create bridges on all of these. So if you couple seconds here versus maybe a couple minutes per the pointy and clicky, and then if we do that MAAS info thing again, let's look at that. You see that we now have that BR0. Now, one part that I didn't do, I didn't move those onto a network itself, so there's not an assigned subnet. This is just what's available. So I'll just run one more command that basically moves those to the subnet that I want. That's the wrong command. I can set so basically what I'm doing here is I'm telling it to give an IP address, BR0, move it to VLAN ID 4, the subnet, and set an MTU of 1500. And if I wanted jumbo frames, I could have done 9,000 or whatnot. So this is running in parallel. It takes a second to do all the things, but you'll see now all of the ENX, and you can see they're all different names and how that would be a challenge if I was trying to use that as my FizzNet.
All right. In the interest of time, we also have a couple of more topics to discuss. So let's move forward.
Yep. So showing a couple of easy demos here. But.
All right. Cool. Thank you. Let me share this back up. There we go. There we are. So as you can see, MAAS is really powerful to automate all of the bare metal steps that are necessary to make it feasible to deploy Kubernetes onto those machines, have like reliable nicknaming, for example, bond adapters that you can rely on. And we went as far actually as building a copy provider for this. So early on in the development of Pallet, which is Spectro Cloud's Kubernetes orchestration platform, we saw how powerful MAAS was for enabling bare metal deployment. And since MAAS provides access to the cloud init configuration for the servers that it deploys, we knew that it could be leveraged to automate the creation of entire Kubernetes clusters. So we built a cluster API provider for MAAS, allowing our platform, Pallet, to natively support it for Kubernetes cluster deployment. As you can see on the screenshot in the left, we can target a specific MAAS resource pool and availability zones in Pallet for the selection of server nodes in each Kubernetes worker pool. We also recently enabled autoscaling support, allowing the cluster to dynamically spin up and down and additional workers as needed by the workload demand. Pallet itself also provides full access to the OS layer configuration, so Ubuntu in this case, where you can pass commands that to be run before and after the Kubernetes cluster is created or joined. And this layer is used to control aspects such as like the internal IP of the cluster node if it has multiple NICs, which you can see in like the addresses here, where we do a call to figure out which particular address is assigned into like a particular bond name that we expect. And then put that in etc default kubelet so that Kubernetes comes up with that as the internal IP of the cluster node. Similar thing for like setting up multipathing. We can lay down entire file content here to make sure that multipath, for example, is fully configured correctly. And anything else that needs to happen at the host OS level, which is not already taken care of by MAAS. And so together, Pallet and MAAS make for a powerful and flexible platform to ensure that clusters get deployed fast and consistent. Let me quickly show that here. So here I have a Kubernetes cluster that is running in Pallet. We're running Kubernetes 126.4, and we have like a bunch of services in there. We have our own cluster profile that manages all of these different additional services. And we can see that we have, in this case, one master node that is using the default resource pool and a default zone and a worker pool of 4 nodes that is in this case also using this. Although we could use different pools I have another one for private gateways, for example. But you could split these out into a dedicated resource pool for master nodes and worker nodes, so that your master nodes could, for example, be a little bit smaller than your worker nodes. Now, if I wanted to just add another server, all I need to do here is just increase the count. So it will go to 5. That will tell Pallet that this worker pool needs to be extended by 1. And so it will tell the agent that is running inside this cluster that it should spin up another node. That translates into a machine spec in cluster API to deploy another node. And that gets translated into a so-called MAAS machine resource, which gets picked up by the CAPI provider for MAAS that is running in this cluster, which will then interact with MAAS to deploy an additional system. And so as soon as MAAS starts deploying a system, it will start filling in the line here to show that a system has been selected from the pool of available hardware, and it has started provisioning, and then we can basically follow the provisioning flow from here automatically. So when it gets picked up, it's somewhere in like a minute or two, we can come back to this and see this happening in action. And then MAAS itself will take one of these ready pools here that are available, that are in the pool. So here it goes. It's now deploying this one that it took from the default pool. And we can see that indeed, so we have MAAS pool 3 that was selected here to do. And we can see that indeed MAAS pool 3 has been used from the pool and is now in the provisioning state, and we're just following MAAS as this goes along. And this makes the entire process just seamless and a joy to work with bare metal hardware this way, because I just don't have to do anything. All right. So, but I mean, don't take it from us, take it from our customers. So Super League Gaming is a leader in creating innovative and immersive entertainment experiences, platform and audience monetization, and dynamic content feeding channels across the world's top gaming platforms. They are best known for Minehut, which is a free Minecraft server hosting solution that allows gamers to host their own Minecraft server, as well as explore thousands of community-built servers. Super League now runs this infrastructure with Pallet and MAAS, serving thousands and thousands of Minecraft gaming sessions on bare metal Kubernetes, using Spectro Cloud Pallet and Canonical MAAS. The infrastructure running these workloads consists of more than 100 physical servers, running an optimized Kubernetes stack tuned for performance. And MAAS provides the flexibility of defining different resource pools of hardware optimized for specific infrastructure roles, like gaming servers and proxy servers and whatnot, as well as the consistency of ensuring that all nodes in these worker pools are deployed with a consistent configuration. If you'd like to learn more about this, please reach out to me afterwards. So coming back to the last option, I promised earlier I would come back to why I named VMware specifically. Let's discuss it a little bit further. So far in this session, we've been talking about what it means to run Kubernetes on bare metal without a virtualization hypervisor layer. And we know that a lot of enterprises are looking more closely at this, particularly after Broadcom's acquisition of VMware sparked worries in the industry. And that may also lead you to think, well, if I can move my containerized workloads off a hypervisor in the data center, can I move my VMs there too? And so while there is some uncertainty on what will happen to VMware and its ecosystem specifically, there's also the reality that virtual machines are here to stay. With every rev of technology advancements, we've seldomly seen the previous technology stack disappear altogether. And so in most cases, the newer technology just becomes 10 times more ubiquitous, but never fully replaces its predecessor. So too will go the fate of virtual machines. So how should we deal with this? Well, as it happens, bare metal Kubernetes can actually handle running virtual machines just fine as well. With a Kubernetes add-on called KubeVirt, we can manage KVM-based virtual machines as if they were regular Kubernetes objects. KVM is a highly mature hypervisor that pretty much every large cloud platform that isn't VMware or Azure is actually running on. With decent storage, networking, and backup solution, you can put together a virtualization cluster on bare metal that runs VMs with the best of them. Automated bare metal deployment plays a big role in this, ensuring that consistent configuration and maximum performance. You'll actually see us announce something more concrete around VM orchestration in a couple weeks, so stay tuned if you want to learn more about that. If we take a look at the new Kubernetes resources that KubeVirt introduces, we can get a glimpse of how this works in practice. The main resource is a virtual machine resource, right here, that defines the specs of your VM. So CPU, memory, networking, BIOS or UEFI boots, storage, run state. And when this VM is started, a virtual machine instance resource is created, which only exists as long as the VM is actually running. And this resource will cause a Virt launcher pod to get spun up, which actually runs the VM process, which is QEMU itself. The pod gets CPU and memory reservations to limit how much it can consume. If we then specify a Multis network via a network attachment definition, if you're using Multis, that will be associated to the Virt launcher pod and give it an additional NIC in that network. So this is a great way of putting NICs directly on VLANs so that you can migrate a VM to a bare metal Kubernetes cluster and keep it with the same name, same IP address, running in the same VLAN as before. KubeVirt also has a concept called data volumes, so using the KubeVirt containerized data importer, which allows the creation of persistent volumes with data imported onto it before it's handed over to the Virt launcher pod. This way, we can, for example, spin up VMs with the OS disk imported as a copy from a central disk template. Running the VMs inside the Kubernetes cluster on bare metal provides some interesting advantages like hybrid workloads. So you can run a VM natively on the Kubernetes pod network, that's the top line here, making it totally inaccessible outside the cluster, and then use a Kubernetes service resource to publish specific ports on the VM to other workloads in the cluster. So here we are publishing port 5432, the Postgres database port, as a service, so that like a pod, an application pod, can access the database. You can also create a service resource of type load balancer, so that it gets an external IP address, so that the service can be accessed by workloads both internal and external to the cluster. So that when you're moving VMs, if you are running these VMs inside the pod network, external applications can still access specific services that you specify this way. Either of these two options shield the VM from most external access, and that dramatically reduces the attack surface to just the services that you decide to publish. Now, a third option is what we talked about earlier, the ability to put a VM directly on a VLAN. So that's here via network attachment, where the entire VM becomes externally accessible. And this is useful for moving a legacy workload from, like, for example, VMware to KubeVirt without having to make any changes to the VM itself. Now, running hybrid workloads is probably going to be the best way of moving to Kubernetes at your own pace without having to refactor all aspects of an application immediately. So some workloads like Postgres, for example, might just be too much work to containerize and make HA in the short term. And just running it as a VM for now makes a lot of sense in that case, as you would leverage like the vMotion capabilities that KubeVirt provides to have high availability of this one database server. And so with those hybrid workloads, you can still run the workload in your Kubernetes cluster and benefit from the unified management of being able to have both VMs and containerized workloads in a single cluster and managed in a single way. All right, that brings us to our last slide. If you want to learn more about the topics discussed here, we have a description of how we integrate with Canonical MAAS, how Spectro Cloud does that for Kubernetes deployment. There's also a blog on bare metal clusters that goes deeper into that. If you want to learn more about how to run virtual machines in bare metal Kubernetes clusters, we recently did a webinar that you can follow there on how we make VMs a first-class citizen in Kubernetes with KubeVirt. And there is a VM management section in our docs that gives you a hint of the new capabilities around virtual machine orchestration that we will be launching in the next couple of weeks. With that, I thank you very much for your attention and your presence, and I wish you a good day. Goodbye.
Thank you, everybody.